Yeah, so thanks for joining. Today we're going to be learning about Rust, the Rust programming language. I think we have a little bit of a mix of experience with Rust. Anthony has written some Rust before, but I believe everyone else has basically zero experience.
Hello World.
Hello World. Okay, we have a Hello World, and then everybody else like this. Okay. So some basic stuff. Okay, cool. So given that we do have some people that have zero experience, I think we'll start from absolutely nothing. And we can do questions, like feel free to interrupt at any time and stuff like that. That's totally cool. And we'll just go through. The goal for today is by the end of the day to build up a hash map implementation. So, you know, if you're familiar with maps or objects in JavaScript or whatever, it's just how does that work, where you can associate a key and a value together, and then later get out a value by its key. It's kind of a little contrived of an example, but it's actually quite interesting when it comes to the features of the Rust. It touches a lot of the different parts. The one thing before we get started with Rust is that unlike a lot of other languages, it is very low level, although at times it can seem quite high level. So that will be interesting. But Rust does care about a lot of things that you don't have to care about in other languages. So if you've never programmed in C or C++ before, some of these concepts might be new or a little bit unfamiliar, but it's all relatively easy stuff, but it just might require a little bit of brain power to kind of wrap your head around it, but it's nothing too challenging. I have here the Rust programming language website that you can go to if you want to find different things. Probably the most useful thing when you're actually writing code is to go to the actual docs, but I usually just Google for things like vector. And it's usually the first thing that pops up. So here's what doc.rustlang.org looks like. So we'll be taking quite a bit of a look into the docs as we go along. But we're going to start with Hello World and then kind of go from there. So the first thing to do when you want to install Rust, what you can go ahead and do kind of separately as we go along here, is to go to rustup.rs. And what rustup is a tool for managing versions and different tool chains for the Rust compiler. So like if you're used to the Node world, for instance, and NVM, for instance, or Ruby world, RVM, it's just a way of, if you want to update the Rust tool chain that you have, you can use this tool. Rust also can cross-compile to different architectures. So if you're on a Mac and you want to build something for Windows, you can, that's a little bit difficult, but there are ways to kind of cross-compile between different architectures, and Rustup allows you to do that as well. So you just have to, if you're willing to trust shell scripts that come from the internet, you can do this. But you can also read it first if you're not so trusting. I would read it first. That's what I'm legally obliged to tell you. Once you have that, what you'll have on your computer then is a tool called Cargo. And Cargo is basically like the build tool and dependency management tool for Rust. And what Cargo ends up calling is Rust C, and Rust C is the Rust compiler. So we won't actually ever use Rust C directly to build things, but just know at the end of the day, like we are using just a plain compiler called Rust C, but we're going to use Cargo because Cargo is great for creating projects, adding dependencies, building, testing, all these kinds of things. That's what we're going to start with first. Are there any questions so far? No? Cool. So to get started, and let me know if something's too small or something like that, I can increase the size of things. To get started, we can just do cargo new, and then the name of our project that we're going to create. So I thought we would just call it something like our hash map. And you can see by default, it creates a binary application. So create a binary application, our hash map. This means literally it's going to create an executable on your machine that you can run. And we're going to stick with this because that just makes it, easy to kind of run and see the output and stuff like that. But you can also create libraries. And in order to do that, you just do --lib, and it will create a library instead. Cool. So we're going to go in here and go into our hash map. And then we can take a look at the structure of the folder here. It's pretty simple. We have cargo.toml. You can take a look at cargo.toml here. Oops. And what cargo.toml is it's just like a package.json kind of thing, a manifest file, it describes your project basically, and it's very simple. Just a name, a version, and an author, an edition, which we'll talk about a little bit later, what an edition is, and then a dependency list. And our dependency list by default is empty, right? We have no dependencies. So very straightforward. If you're not familiar with TOML, it's just a file format that's kind of similar-ish to YAML, but fixes a lot of the issues that YAML has, which there are many. And it's not very hard to get used to. Then we have a source file, or source directory rather, and in that source directory we have main.rs, where our code will go, and we're going to open this up inside of VS Code here. Using VS Code for Rust, the support is pretty good. I've also used Vim with Rust, which is great. You can use, I know CLion from JetBrains has support as well that is supposed to be good. I haven't personally used it myself. You can use other editors and stuff like that, but the tooling might vary, depending. I've heard, for instance, that Visual Studio, playing Visual Studio is not super wonderful with Rust, but you might have better luck. So cool. We can take a look at main.rs here. Can everybody see that? Awesome. And here is our hello world. It's already written for us, so we don't even have to write it. That was pretty easy. We have a main function, and main function, just like in other languages like C, for instance, gets called by default in a binary. And we call the print line macro. We'll talk about macros later on. For now, you can just think macros as functions. They just have a little bit of extra capability, and we pass in the string hello world, and it will print to the screen. So pretty straightforward. If we want to go ahead and run it, we can use cargo again to call cargo run. And cargo run will build it and then run it, and it prints out hello world to the screen. If you just want to build the thing, you can call cargo build. And then you'll notice that now we have a target folder here, and that target folder will have a debug folder inside of it, and then here's our executable here. And there's a bunch of other debug symbols and stuff like that, different things in there that you can use, but here's our executable right here. And you can, if you have a friend who also has a Mac, you can just pass it over to them, and it should work. Basically, it's only dynamically linking in things that you're pretty sure you're going to have on a Mac, like the system allocator, for instance. Cool. So that's Hello World. We know Hello World now. Are there any questions?
I think we're pretty good on Rust.
Cool. All right. So thank you very much. So I know we're all really interested to get into actually writing some code, but I do want to take 1 or 2 minutes to talk about why Rust is an actual interesting language to learn. There are a lot of languages that you can learn, but Rust I think is an interesting one to pick for various reasons. Like I said earlier, it's an extremely low level language. So if you're interested in things like high performance or running on computers with not a lot of resources on them, so like embedded devices and stuff like that, you can't very easily or very performantly put things like Node on them because running V8 takes a lot. And of course, like there are embedded devices that have JavaScript runtimes on them, so it's not impossible, but at some point it gets to be too much. And so you might want to use something like Rust. Also, if you're going to be writing shared code, for instance, if you want to write things on once and then run them on many devices, traditionally at Microsoft, for instance, we've used C++ a bunch. Rust is an alternative to that. You can just run it, compile it for the different architectures, and then because it doesn't really have a runtime other than needing an allocator, a memory allocator, basically. You won't really notice that it's there. Unlike, for instance, if you want to use React Native or something and you have to use an entire JavaScript runtime, like that is a much larger hit there. So Rust is quite fast. You may not notice it being fast if you just create a binary and then start running it with cargo run. The reason is because it by default compiles in development mode, so it doesn't have a lot of the optimizations. If you want to run things in release mode, you can pass -- release, and it will compile it with all the optimizations, and our hello world is like extra fast now. So that's good. Any questions about why Rust or why we're here today?
No, just a quick question. So it's a low level, it's fast. Do you have any comparisons to C++ regarding performance?
Regarding performance, so all performance measures need to be taken with a very large grain of salt, right? So it's really difficult to say exactly, how they compare, but there are like large suites of benchmark testings and stuff out there, and by and large, Rust either performs in line with C++ or beats it.
In modern C++, I think Rust does very, very well compared to modern C++.
Yeah, those C++ benches are usually actually just C with a few features from C++ thrown in, because if you use a lot of the modern features, it's not really, it's not usually as performant as you would get if you were to write plain C. I would wager, and I don't have a ton of evidence to back this up, so it's something we, to look into, but I would bet that kind of idiomatic Rust versus idiomatic C++ 17, Rust probably is going to be faster generally.
Right. So Rust is a good contender, for example, in audio engine, writing an audio engine.
Yes.
All right.
Yes.
Especially because like the runtime is very, very small in Rust. And so it has predictable performance, which a lot of languages don't have.
Yeah. And an audio engine is something interesting to bring up. I can point you to a talk where some PhD students basically were looking into writing drivers, like userland drivers, in different languages, because you can write userland drivers in anything basically. So they wrote them in JavaScript, in C#, in Java, in Haskell, and in C, and in Rust, and kind of compare the development experience and the runtime performance and stuff like that. And one interesting thing was looking at Go, C#, and Rust, 3 quite fast languages. And for a large chunk of, like for the 99th percentile, basically those 3 languages performed in step with one another.
Yeah.
And it wasn't until you zoomed into the 99th percentile and looked at it that you noticed that Go and C# just shot up in terms of how long they took, generally because of garbage collection pauses and stuff like that. And Rust just chugged along, it was very predictably linearly growing in terms of performance, whereas C# and Go just kind of took off in a exponential fashion at the end there. So it depends on your use case, right? Like, you know, if you're going to be writing something simple or whatever, where performance isn't a huge concern, you know, maybe you don't want to pay the cognitive overhead to use Rust. But if it's something where you think, well, I would use C++ for this, or I would use C for this, Rust is definitely a good alternative. And arguably, and I'm extremely biased here, but I would say you shouldn't write it in C++ or C. You should write it in Rust, because there's a whole class of bugs that are just impossible to write in Rust that are possible to write in C and C++, even modern C++. And we'll take a look at a lot of those later on. Cool. One last thing to mention, the reason that Rust was kind of created, for instance, was to have a safer alternative for C++ for Firefox. So, you know, if you're going to write a browser, for instance, you have always traditionally gone for C or C++, and now Rust is definitely an alternative for that. Cool. All right, so we can get started then. We're kind of, I guess we're going to do this in a little bit of a, not really a test first fashion, but kind of a run first fashion. We want to write out our code like we want it to run in main, and then it won't compile, and we'll kind of make it compile and go from there. And so I guess the first thing that we want to do is create our hash map, right? So inside of main here, let me expand this out a little bit. Inside of main here, maybe we want to have something like let map equals R map. And now we can take a look at the syntax here. So if you want to bind to a variable, for instance, you have let there, and it's pretty similar-ish to a lot of other C-like languages. If you want to call like a static function, like new is a static function on this R map struct that we're going to look at, you just do : : for instance, and all lines that are kind of statement-like end in a semicolon. And we'll see where we don't need a semicolon later on. And of course, it's going to complain at us that it has no idea what RMAP is. So fail to resolve, you know, use of undeclared type or module RMAP. What the heck is RMAP here? So we're going to have to define that. Any questions so far about the syntax or anything like that? Cool. So now we're going to want to go ahead and define our map. So Rust is not really an object-oriented language. You can do some object-oriented type things inside of it. But if you try and get too object-oriented with it, you'll run into trouble. And it doesn't have inheritance and stuff like that. So it's much more like C in that regard. What you do have is structs or structured elements here. So we can create our struct, our map. This is the syntax for creating there. And our map, and I misspelled it to outmap. Our map has no fields in it, so it's just an empty struct.
And so for naming, it looks like the files are all lowercase with hyphens in between, like, but then the struct names are camel case.
Yeah. Yep.
And then function names would be a snake case.
Snake case, yeah. Yeah. And we'll see that in a little bit. Cool. So it's still complaining at us and saying, hey, we've got no function or associated item named new found for our map. So we haven't defined new, which is obvious right here. I'm going to show you what that looks like on the command line as well. So you can see what the compiler errors look like here. Compiler errors in Rust, I think, are really good. So if you ever, VS Code does a pretty good job of showing them to you, but sometimes, you know, it's not quite perfect. And sometimes things get cut off that shouldn't be cut off and stuff like that. So if you ever find a confusing error message, just run it in the console and see if you get better output there. 9 times out of 10, it will clarify the thing. And only once in a while will you be like, I have no idea what that means. And if you find something that's like really weird or something like that, then you should file an issue because the Rust team takes error messages pretty seriously. So we're going to want to go ahead and define a new static or associated function on our map so that we can, so that this will actually work. So in order to do that, we're going to start with an impl block or an implementation block. So unlike in a lot of languages where you kind of like define methods in line with the class or the struct, in Rust, you do that separately, like this, impl our map.
So like a header and implemented running object in C, for example.
Yeah, it's almost always, and in fact, I would wager to say it is always in the same file. I'm not sure if it needs to be in the same file. It might actually need to be in the same file. That's something I'm not sure, but it always is basically one after the other, just like we have here.
All right, so in the same file, but the concept is the same as you have a separate header, then.
I would say no. The reason why is because we're going to actually implement them in place. So we won't do something like this where we say, well, we're going to have a function called new, and then here we're going to implement that function here. That's not how it works. It's literally
All right.
like this.
Okay.
Cool. So we have a new function, and it's going to return our map to us. So this is the function syntax with fn and parentheses, and your arguments we'll look at later go in here, and you have the return value specified by an arrow, our map here. And it's complaining at us for a reason that hopefully is clear to everybody. The error message might be a little bit different than you would expect, and I can show it to you here again. I gotta save the file in order for it to. So you can see here, the new function expected the struct our map, but found open parentheses, close parentheses. And I mean, the reason for that is kind of obvious, right? We're not actually returning our map from this function, right? But it's important to know what this type, open parentheses, close parentheses is. That's called the unit type. If you're not familiar with languages that have unit, it's similar to void, except that it's an actual value. So its type is called unit, and it has one value, also called unit. And basically what it represents is like nothing. Like it's just nothing. So we've returned void out, we've returned unit. And by default, functions return unit. So we need to instead return our map. And it's pretty easy to do that. We can go in here and just go our map like this. And now everything should compile. And it does. You can see up here, we're getting a warning right here. That's the squiggly green line here. And you can say, hey, you've got an unused variable map. You can turn that off by basically putting a marker above that says I want to allow unused variables, or you can do underscore map, or even just an underscore, and then it will ignore the value. But Rust tries to catch kind of these simple mistakes when you don't use things. So is there any questions so far? We have a compiling program, so so far we're doing well. We can run it actually. Of course, not really going to do anything. And in fact, probably all of this will just get optimized away. Any questions?
I explained what functions for Visual Studio.
Oh yeah, I should mention that real quick, what extensions I'm using. There's really only one that is Rust specific that I'm using. And it's this Rust RLS, Rust language server extension. And that's what's giving the kind of the squiggly lines and the code completion and stuff like that. So it's definitely one you're going to want to check out, and it should install everything for you once. I think it requires that you have Rust up on your machine, but after that, it will take care of installing everything else for you.
like how it was notification.
Yeah. Yeah, if all is told, it's not clear, that's.
Cool. And RLS is pretty good. It's still not perfect, but I use it day in and day out, and like probably once a day, I have to like, it gets confused, and I might have to like close a file or something like that and reopen it. But you know, it's fine. Tooling is definitely something that I hope that should get better over time.
Is the language that they used by the extension a common one that you would find in other type use for Rust?
Yeah, I think the JetBrains one, they have, because I don't know, they have way too much time on their hands and decided to implement their own. I think they've implemented like large chunks of the compiler basically to run it.
Yeah.
Yeah, the language server can be used, like it's used in Visual Studio, the main one. It could be used in JetBrains as well. It's Visual Studio Code, like in Microsoft, have specified a protocol for, if you're familiar with the language server protocol, and this is just an implementation of it for Rust. So any place that understands language protocols, like I think Atom and Sublime already have support for this, they should be able to take advantage of this as well. So, cool. All right. Okay, so we have a map. Doesn't do anything yet. So I guess we should go on. The next thing to do probably is to like put something in the map, right? And I think probably what we want to have is map.insert, maybe is a good one. And it'll take some kind of key. Let's do, I don't know. How about like it will go from, for now we'll just do numbers to numbers. And we'll see how that goes. In the future, what we'll do is create another map and have it do some other types instead. But doing numbers will make things a bit easier for now. Cool. So pretty obvious what the error will be here, no method name insert. So we should probably implement that. Okay, we're gonna go down here and do insert this. And we're gonna get another error message here. And it's the same error message that we had, right? But here's a cool thing. It said, found the following associated functions to be used. So if you could look at it here, it's found the following. So we found this candidate is defined on our map here, insert. We found an insert, but it's not a method, right? So we need to make this thing a method instead. So right now it's basically just an associated function or a static function if you want to call it. But we need it to be a method instead. And in order to do it, all the Python people in the room will be happy to do it like this, where we pass in self or this from other languages into the function. Let's see what the error is now. The error says this function takes 0 parameters, but 2 parameters were supplied, which is true, right? We're not taking any parameters here, so we should probably do that. And we'll go ahead and say we're going to have a key. And for now, and here's kind of our first taste of low-level nature of Rust. When we're talking about numbers in Rust, we have to be very specific of what type of numbers we mean, because when you're dealing in low-level things on the machine, the computer really cares what numbers you mean. Do you mean numbers that fit inside of 8 bits? Do you mean numbers that fit inside 32 bits? Yeah. So we have to be specific with that. And there's a way to say like, well, just decide for me. But for now, I think what we'll do is we'll say this thing is going to take in a unsigned 64-bit integer as the key, and as the value, it's going to take a signed, would be a signed 8-bit value, let's say, like this. So here's the syntax of these types, U meaning unsigned, 64 meaning 64-bit, and then I meaning integer or signed integer, and 8 for 8-bit. So if you're unfamiliar with what the difference is between an 8-bit value and a 64-bit value, it's something to kind of look into, but basically it's how many bits does it take to represent this number. Any questions so far? Cool. And we're getting some warnings here saying, you know, we're not using key or we're not using value, which is true, but it does compile, and you know, we can run it, and it ran, didn't do anything, but it ran, so that's good. I guess what we'll do right now is kind of map out what else we want this thing to do real quick, and then we can start getting into the implementation because it won't work basically. So we want to be able to say map.get 1, and then we should get out something like you know, let's say let value equals, and we should be able to say let's assert that value is equal to 2. Does this make sense to everybody? We're going to get a value from the map, and we're going to assert that it's equal to 2, right? Pretty straightforward. And of course, we get an error saying that there's no get on our thing. It's, you know, it's trying to be helpful and saying, you know, there are some things like if you implement some traits, which are interfaces, which we'll get to later, you know, you might be able to get this this method here, but you know, I can't find anything. So what we really need to do is go ahead and implement it. And again, we're going to go ahead and say get self. And I guess we wanted to return an I8 here. And, you know, already it's going to complain, say, you know, you're returning unit and I need an I8. So we can make it shut up by putting in 0 here. And this needs to, oh yeah, so it's saying now this function takes 0 parameters, but 1 was supplied, so we don't take any parameters outside itself. We need to actually take 1. Oops. Well, let's do that now and say this is going to be our key, and it's going to be 64-bit unsigned integer. And now it should be working, right? So we're going to run it to our first instance of probably the hardest part about learning Rust, but the thing that makes it really special. And let's take a look over here what the error actually is. Okay. So we have an error where it says value used here after move. And the value was moved here. So now we're going to get into the borrow checker and move semantics and borrow semantics. And this is basically how Rust gets around not having to have a garbage collector. And by what I mean by not having a garbage collector is garbage collection in the widest sense of the word. So it doesn't have a garbage collector like a tracing garbage collector like Java does. It doesn't have garbage collection like Swift or Objective-C does with reference counting. You can opt into that for certain things, but by default, everything is just basically malloc and free. That's it. But unlike C, and similar to C++, malloc and free is done for you automatically. But in Rust, it's done in such a way that you can never screw it up, basically. So let's take a break from what we were doing real quick and look at a function, foo. We're going to define a function foo here. And we're going to have something like, you know, bar is equal to 1 here. So we just have bar and it's sitting on the stack and it's not doing anything for us. But we want to return a pointer to it, basically. So we want to return, instead of returning bar itself, we want to return the address at which bar is sitting at. So if you're familiar with C and C++, this should be familiar to you. And Rust, we can do that with a little syntax like this. And we're going to say, hey, we're going to return a reference to, and, let's say an U64. So, and Rust, by the way, I don't think we went over this. Like you can write return like this, but you don't have to. By default, everything that the last line of a function, if you don't have a semicolon at the end, will just return from the function. So an implicit return there. The community definitely kind of supports this style. So you might get funny looks if you try and do return. And in fact, I think with Rust format, it gets rid of them, maybe? No, it doesn't. So, but there are like linting tools that will tell you shouldn't do that. But really, it is up to you. That's true. We're getting an error message already because our syntax is a little bit off. So I'm just going to do something real quick. Don't mind this for now. We'll get back to it in a minute. Just say it. Yeah, we'll get there in a second. But basically, if we go ahead. We need to get rid of this. Cool. So now we're getting an error. In C, in plain C, right? You can do this. You can return a pointer to something that sits on the stack, right? That's totally allowed. Except it shouldn't be allowed because it can never work, right? As soon as this function returns, the thing that's this local variable here will just be blasted away. And in kind of more technical parlance, the stack frame will go away and this thing will no longer exist. So if you're pointing to it, it's going to be pointing to garbage memory, right? So you shouldn't be able to do this. Does that make sense? Why you should not be allowed? Any questions there? Why that should not be allowed? Cool. And in fact, in Rust, it's not. So we're saying cannot return reference to local variable bar, returns a reference to data owned by the current function. And that's the key here in Rust, is that every piece of data has an owner. And we can kind of think about it through a metaphor of a book, right? I own a book. It's fine for me to hold on to this book. And as soon as I go away, like, you can't be looking at my book anyway. I'm taking it with me, like I'm going away with it. It's my book. I'm owning it.
And you're a jerk.
And I'm a jerk. So we can have things like, let's say, we'll have a function do stuff, and it's going to take an arg1, and that's going to be a string like this. And maybe we want to do something with the string, like, arg1 plus, or what's a good thing to do on a string? Let's see here. We can extend it. Interesting. Let's see. I think we can lower, to lowercase here. So this is fine here. Like, we can do this. It's saying, we're not returning it before. We should pick something on string that mutates string, that actually changes instead of returning a new one. That would be good. This is a good chance to take a look at the docs. We can explore a little bit. And I'm trying to avoid one thing about, let's do that. Let's do this. this avoids a little bit of the complexities of string for now. Push a string on here, and this just mutates the string in place. So we're going to push, like, you know, it's going to make the string very excited, basically. And this just mutates it in place. If we mutate something, by the way, in Rust, we have to mark it as mutable, which is really nice. So you have to, like, you can't, if things are, oops. Oh, sorry, it's here. You can't just mutate things willy-nilly. You have to say this thing is going to be mutated, and it's really nice for documentation and stuff like that. So if you look at the function signature of something, you can tell whether it's going to be mutated or not. That's comes in quite handy here. So this is great. You know, maybe we have another function here. I'm going to create a string, my string, and just look over the fact that I have to do string new here. I have my string here, and we want to do stuff, and let's say, like, let's change this to make excited. So make excited my string. This is going to be great. We're going to have hello with a bunch of exclamation points on it. That's going to be awesome. There's anyone here? Oh, I think I didn't want to have to talk about this, but we will have to in a little bit. I have to write toString here, and I know you're thinking that is already a string. Why do I have to call toString on it? We'll get to that in a minute. But just know we have a string here. We're going to pass it to make excited. It's going to put a bunch of exclamation points on it, and then we're going to have, you know, my string that is hello with a bunch of exclamation points on it. That's going to be awesome. So, like, let's print that out to the, you know, to the console. And we can say that our reading is string. Oops, my Vim extension died apparently. So in most languages, this will work, right? This is totally fine. But we're creating an error here. And it's saying borrow of moved value my string. Value borrowed here after move. So we can take a look here. This looks like. Oops, gotta save the file first. So we're taking our string, you know, just like we have a book, and we're passing it to another person. We're passing it to this make excited function. The make excited function now owns that string. We've passed our book onto it, and now we, in this function here, another function right here, we no longer own that book. So we can't do anything with it. We've given it away. Once I give you my book, I can no longer lend that book out to Raymond, right? It's not my book to lend. And so that's what it's complaining about. It's saying, you've given this string to this function. That function might make excited now owns that string. You no longer can use that string anymore. And what this prevents basically is using a value after you've already given it to somebody else. The great thing about this is only one variable or function can own a value at a time. And what that guarantees is if only one thing can own a value at a time, one thing can destroy that value. And that guarantees that when that value goes out of scope, we can run the destructor on it. We can call free, you know, to give back the system memory. And we know we have statically verified that only one thing will call that free function. And if you're familiar with C and C++, this is awesome because in C especially, if you call free twice, something will happen. Something. And like literally I mean something because it's undefined.
Like, yeah, something or nothing will
Yeah.
Yeah.
Yeah. It could continue working, but on the next run, maybe it crashes. Like literally, it's up to the compiler, it's up to what's happening on your machine, like literally the weather outside might affect this thing. It's that undefined, you have no idea. So in order to make it very easy to understand, and Rust, only one thing owns a variable at a time, and that means only one variable, when it goes out of scope, will deallocate that thing. And so you can never run into an issue of use after free, meaning after you've freed a value, I use it again. You can never run into double free, which is another C mistake that people make, where you call free twice on something to try and free it. You cannot, that is not possible.
Zombies. Is it possible to have zombies in Rust if you're not using unstatic state?
What do you
What do you mean? Objects that continue, objects for whom memory has been allocated, values for which memory has been allocated on the heap, but there are no references to that memory anymore. You can't access it.
So in general, memory leaking memory is considered safe. What that means is, although it is an unfortunate thing, and you probably don't want to do it, it is not memory unsafety. And so in Rust, in general, memory leaks are possible, although given given more mechanisms that we talked about right here, it's way less likely to happen. So yes, memory leaks are technically possible to have in safe Rust, but you will run into them a lot less often than you would even in garbage collector languages. So when you're thinking about, that's a good point, when you're thinking about the guarantees that the borrow checker will give you, you can really think oftentimes in terms of the guarantees that a garbage collector gives you. Mm-hmm. So garbage collectors means that, like in a JavaScript or in Java, you don't have to worry about use after free, you don't have to worry about double free, you don't have to worry about any of these things, because the garbage collector takes care of it for you, right? Yeah. It scans the heap and looks and says, okay, if this thing is this thing still being referenced somewhere, or somebody's still holding on to this thing? Oh, so nothing is referencing this thing anymore, let's get rid of it. But a garbage collector does not guarantee against memory leaks, right? You might have, one thing pointing, you might have a cycle, for instance. One thing points at another thing, that thing points back, and then those things just lock onto each other, and although nothing else in the program is referring to them, they're just going to stay out. And so those types of things are not necessarily covered by the garbage collector. But over time, you'll see why it's a lot less likely that you'll have. So I just want to make sure everybody understands this error message here. What the error message is saying is we're trying to borrow a value, we're trying to use this value, but we don't own it anymore. My string doesn't own that string anymore. It's been passed, the ownership has been passed into make excited. So now here, arg1 owns that string. That piece of memory is owned by arg1. And what that means is when that arg1 goes out of scope, right here at line 30, it will be deallocated. So we know exactly, statically, when arg1 will be deallocated. And it's right here at line 30.
Now, I have a question. Yeah. So I know how we're going to solve this, but I have a question. If we return so if we change the function signature for make excited to be arrow string, right? And then on line 30, we return arg1. It will just be moved back. There will be no copies. And we just have to, we'll shadow the variable in the calling function. Yeah. Like that is a way to solve this problem.
Yeah, right? So let's solve it that way, right? Let's go ahead and say, well, we would really like to use my string again here. can do something that says, let my string, and variable shadowing in Rust is fine. You can,
Right.
as long as you say let again, you can reuse names that are above. And my string is always that below this line going to refer to what was returned from make excited. This thing is basically no longer available to the rest of the function. And right now it's complaining, it's saying my string is unit. That makes sense. We're, by default functions return units, so we have to say this thing is going to return a string here. Now it's going to complain, hey, you're not returning a string. Yeah, I expected type string. I got unit instead.
Does anyone have a chart?
I have a chart.
You might. Why don't you use that? Okay.
My ancient MacBook battery.
I know how it is. All right. So now we're going to mutate arg1 and we're going to pass it back out of the function. We're going to return it. We're going to store the thing in a shadow variable. And of course we can name it something else like wow here. And as long as we use wow here now, this will all work. We're getting some warnings because it's never, these functions are never used anywhere else in our program. So it knows like, hey, you're not actually doing anything here. But other than that, this is going to compile fine. In fact, we can go ahead and show that. It's compiled, it ran, it's fine.
Quick question, because I think I just missed it. Yeah. Why do we have this list to write arg1 on the last one for the third?
Because if you were to do this, like this right here, push stir right here, returns unit, like because it modifies arg1 in place. It mutates arg1 in place. So if you want to say it in another language's terms, like it returns void, or it doesn't return anything basically. So right here, like this is just, and it's going to say it right here, found type unit, but expected type string. So we have to return arg1 here. So this is all good. Like this works, and like Anthony was asking about, what this will do is, arg1 has ownership of that string that we had. It's going to mutate it, and then it's going to pass ownership back. So it's basically like saying, I have a book. I hand that book to Peter. Peter can do whatever he wants to do with that book. It's his book. He owns it. So if he wants to rip a page out or scribble in it or whatever, he's totally fine to do that. He owns that book. But then he can give that book back to me. And now I can do whatever I want, but Peter can't do anything with it anymore, right? So now it's, I can scribble in it or whatever, and I'm free to pass it on to somebody else if I want to.
But to be fair, I think here we just say that I will give back a book, but not specifically the same book. So I can give you another book back.
That's true. That is absolutely true, yeah.
Is there a way to mark the argument? Something that I necessarily, so after the return of the function, we return back to.
That is the exact same thing before? No, there's not. But there's a mechanism that we're going to talk about called borrowing that will get around all of this and effectively allow you to do that, guys. So kind of going along with what Peter was just saying, like this is a little bit annoying and weird, right? Sometimes you just want to like lend somebody your book and say, hey, you can read this thing, or even like, here, you could write in this thing, you can do whatever, take notes, that's totally fine, rip pages out if you need to, but I just want it back at some point. That's all. Like, and there's a way to do that. So we're gonna change this function instead to basically to borrow that string instead of taking full ownership of it. And the way to do that is by this syntax here, where you do ampersand mut. And what ampersand means is, it says this is a reference.
Yeah.
This isn't the actual string, it's just a pointer to the string, right? And mut here says it's mutable. This thing is if you don't do it here, you do this instead, which this is also valid, it's immutable.
Oh.
Meaning In the book analogy, if you do it like this with just ampersand, if I hand you the book, I'm basically saying to you, feel free to read it, just don't write in it. Don't touch it, don't change it. You can read it all you want, and when you're done, I'll take it back. If I do this instead, understand, but what I'm saying is, I'll lend it to you, write in it, read it, change it, rip pages out, doesn't matter. I'm just gonna have, I still am the owner, so like, I'll need it back when you're done, kind of thing. And so if we take an immutable reference like this, we actually don't need to return the string anymore, because we can just mutate it in place. And make excited doesn't return anything now anymore. And so we can just go ahead and use this. So we're gonna have one last, this basically works right here. We have one last error, and that's basically saying, hey, you've passed in a string, an owned string. You have tried to give ownership to make excited, but make excited doesn't want ownership, it just wants to mutably borrow. That's all. And so in order to do that, we just do the ampersand let here and say, hey, I'm not handing you ownership of my string, I'm just handing you a mutable reference to it. We get one last error, which is saying you can't mutably borrow something unless it's marked as being mutable, right? Again, Rust is says you gotta tell it, like, if you don't mark things as mutable, it's assumed to be immutable, which is very different than almost every other language, especially older languages where everything is mutable by default. And if you want it to be immutable, you have to mark it as immutable, right? Think of like const and stuff in JavaScript, for instance. It's the exact opposite of Rust. Everything is constant until you mark it as mutable. And so we can just do that up here and say, my string is we're gonna mutate it at some point, like that. And you don't have to mark that as mutable since we're already marking it as mutable here.
Yeah, one.
Yeah. And this works. Like we are good to go. Like, so we have taken my string and we have passed a mutable reference to it. We have allowed make excited to borrow it mutably, but we still own it. So can anybody tell me where they think that this variable will be deallocated, where it will be destroyed? Where specifically this string, this piece of memory right here.
Line 27.
Line 26, you mean, right? Yeah. Yes, that is correct, but can you tell me why?
Well, we allocated string on the stack. We passed the reference to another function. It did whatever it wanted to, but the reference was still here. We printed it, and the scope goes away. So
yeah, exactly. So unlike before, where we were passing ownership to make excited, and make excited was now the owner and was responsible for deallocating. Remember, there's only one owner, only ever one owner, and that owner is responsible for deallocating that memory. We didn't give ownership to make excited. We just said, here's a mutable reference to it. We still own it, which means we're still in charge. And by we, I mean another function here, this one right here, is still in charge of that memory. And when it is done with it, when the variable that owns it, and really it's like this my string variable is the owner right here. When that goes out of scope, then it's deallocated. Does that make sense? If you understand, if you're not fully rocking it, it's okay. This is like the reason that people get frustrated with Rust is this right here. If you can understand this, you're golden.
This is much cleaner than C++.
Yes, I agree. If you've done C++ before, all of this is like half implicit, half explicit. It's very confusing. In Rust, it's very clear exactly what's happening. You just have to know the rules. And again, like if, let's say we don't actually want to mutate and make excited. Let's say like make excited instead wants to print out you know, hello, and then our string. And like printing doesn't mutate the string, like it doesn't change it at all. So we don't, you know, we can do it like this. This is totally fine. Sorry, it's called arg1. This is totally fine to do, and will work. But like it's being a little bit aggressive here. Like, you know, I'm telling Peter is requesting to have this this book, this string, and he's requesting like you know write access to it. But all he's going to do is read it. Like, probably a bit greedy, right? So we can just do it like this. We can just do ampersand string here, and that says it's not a mutable reference. It's just a mutable one. You're allowed to read as much as you want, but you can't write. This is probably, you know, this works. This is the better way to do it. And what this means now is that, you know, we're not allowed to mutate it in here. So again, like if we tried to mutate it, we would get an error right here and say, hey, can't borrow arg1 is mutable. It's behind the ampersand reference, behind just an immutable reference. You know, you can't do that. You need to make it cannot be borrowed as mutable if it's already borrowed as immutable, right? So that's not allowed. So that's borrowing at you know the high level first steps. There's one more thing that's very important to know that kind of makes this all work, and it's kind of a logical conclusion to what we've already talked about, and that's how many references of each type you're allowed to give out, right? This is where the book analogy kind of breaks down. So if I have a piece of memory and I give an immutable reference to Peter, the Peter function, I can also give an immutable reference to Sigurd. So that's allowed. So you can have as many immutable references passed out at one time as you want. It's totally allowed. As many readers as you want. But I cannot then pass out a mutable reference at that same time. So the rule is as many immutable references as you want, or exclusively one mutable reference. And there's a whole bunch of computer science stuff that you may or may not be familiar where this also applies, where you're allowed to have many readers. There's like read-write locks, for instance, where you're allowed to have as many readers as you want, but not a writer, or one writer at a time. It's the same concept here.
How would you get into a case where you're passing two references at the same time? Is that like parameters on a function? Or?
Yeah, parameters on a function is a good example. Like let's say like arg1, arg2. These are terrible names, and I super apologize. We'll go ahead and print out. You know, we'll print out both. Complain here. Using it. There we go. So okay, let's go ahead and pass it. Let's pass my string in again. A bit contrived, right, that we're going to do it here, but like we can also, we can imagine right afterwards that there's another make excited, and we're going to use, an immutable reference again. Like that's probably a better example there. We'll look at that in a second. So this works fine. Like you can run it. But let's switch back here to where we have this, and we're going to push, exclamation points onto both of our strings here. We're going to make this mutable. We're going to make this one mutable too. Oops. And now it's going to blow up. It's going to say, oh no. First, of course, you might think, well, we got to make these mutable now. But it's going to complain. And it's going to complain exactly with what we would expect. When I say, you cannot borrow my string as mutable more than once at a time. Very straightforward. And when you look at it on the command line, it shows it very clearly and says, second mutable borrow occurs right here. First mutable borrow occurs right here. Can't do that, right? You know, maybe a more straightforward example is this. Let's get rid of these. This actually works right here. It used to not work. This works here because it's smart enough to know that we've mutably borrowed it just until here. And once we reach this next line right here, the mutable borrow is over, right? We have, you know, it's used the whole thing, it's returned, so we know that this is safe. So that's fine. But we'll see in future cases where less contrived examples will actually work. Any questions about that? We're going to get back into our hash map because now that we understand borrowing, we're able to do a lot of things. So we can go back here and we can kind of read our error message again and understand it a whole lot better. So it's going to say here, hey, you've used a moved value. Moved means you've given ownership of it to another thing. That's what moved means. You've moved this value map, you've given ownership of the value map away to somebody, and now you're trying to use it. You can't use something that you gave ownership away to.
By giving that away, is that by itself?
Exactly. Exactly. So we see here, given this self right here, it's not, you know, and we'll see in a minute, there's ampersand self, there's ampersand what self. So there are different ways to explain the ownership of self here. Self is just like any other argument. It's just a different syntax. You know, they could have picked this syntax where you had to explicitly name, you know, self as our map and stuff like that or something like that. But, you know, it's just a different syntax, but the rules that apply to self are the exact same that apply to everything else. So if you pass in just self, it means you're passing ownership of self into that function.
Passing ownership, and it's also immutable in this case.
So the thing with when you pass in ownership is you've passed ownership, so you can do whatever you want. I mean, if you were to actually mutate it, I believe you. No, you don't have to mark it as one. But you know, if you own the thing, you can do whatever the hell you want, right? So when we call map.insert, and again, like maybe I should show this to you. Map.insert is really syntax sugar around our map. Insert map, you know, 1, 2. These two are totally equivalent to each other in every way.
Which is interesting. That's exactly what it is with those two.
Yeah. I think a lot of languages are like that, right? And is one of the arguments for this kind of syntax, and the kind of Pythonista argument for it as well, is that like, well, you know, we're being a little bit more explicit. We're de-sugaring a little bit for you. So map.insert, we've moved map into the insert function, or another way to say it is the insert function has assumed ownership over map, over the thing that map was referring to, right? And so now right here it says, hey, you gave that away. Like you can't use it anymore. That's not allowed, right? And so does anybody know how to fix this? We have all the tools to be able to fix it.
Mark self is horrible.
Okay, 100%. The question is, we have two types of references, two types of bars, right? We have immutable and mutable. Which one should we use?
This is a service should be immutable.
Yep. So the way to fix this is to take self by a mutable reference right here. And
We have to make one.
yeah, yeah. So it's going to complain one more, and that's exactly what Peter was just saying. Well, we cannot borrow map as mutable because it's not declared as mutable. So like again, unless we specify everything in Rust is immutable, so we got to say no, actually it's not. It's mutable. And now it will compile. Ta-da! This is great. This is wonderful. Of course, we have one more problem, right? If we want to do get multiple times, right? We have the same issue here, and this is the same exact issue, right? It says use of move value map, because value, and again, it's much clearer when you run it on the terminal, value was moved on line 4, and then value was used again on line 5. You can't do that, right? So like, you know, very similar fix. What are we gonna do here? Anybody?
Should I answer? Or?
Yeah, let's have Raymond answer. I'm gonna put him on the spot.
Okay. We need to, well, I don't think we need to do the reference. Just need to know reference.
Yeah. Cool. So we're just gonna make it gold star, yeah. So we're gonna make that an immutable reference, and now everything will work. We're gonna need a warning because we're not using value 2, but like everything's gonna compile and everybody's gonna be happy, right? We actually had, we did something. It ran. We panicked because our assertion failed. Value is not equal to 2. It's equal to 0, right? Because we're hard coding. So, but this is great. We're like now in the realm of like how to implement a hash map, and out of the realm of like what the heck is going on with Rust, right? This is good. Any questions about that? Like all of the difficulty of Rust is because of things that come out of this. Like, you know, this is a very simple program, right? Like imagine writing a video game or something like with these rules. Like the one thing that Rust enforces on you is that you bend to its rules. Like if you do things the way that Rust wants you to do them, you will be a happy person. You will get performant code. There's a great talk by Brian Cantrell, he's the author of dtrace, which is like a performance tool, and longtime C programmer, picked up Rust, I think about 8 months ago or something, and fell in love with it. And his first experience, he tells it, was hilarious. He starts rewriting a piece of C code 1-to-1 in Rust, tries to do it, and it uses like a doubly linked list, which is quite common in C, but like extremely difficult to do in Rust, because a doubly linked list, you have 2 owners, right? You have like the node here points back to a previous node, and the previous node points to the next node, so they're both like pointing at each other. Like Rust is like, I can't, like, yeah. So like he's banging away at it, and like, you know, the borrow checker is just throwing up in his face and saying, no, dude, you can't do that. And he finally says, you know what? This is getting ridiculous. I'm just going to get it to work. I'm going to write it in the naive way that is, you know, it's going to be way less performant, but it's, you know, at least I'll get it to compile and I'll be able to run it and I'll see how much slower it is. So he does it, rewrites it in the naive way without a doubly linked list, using B-tree hash maps, I think, and runs it. And to his surprise, it's faster than the C version. And that is the story of Rust. If you do it the way that it wants you to do, you will get fast code. It will be happy. Everybody will be smiling and laughing, but you got to do it the way that it expects you to do it. That's the only thing. Cool. Any questions so far?
I have like a idiomatic question, because we're dealing with mutable values and immutable values with the common convention to be just use immutable values everywhere, or to use mutable values everywhere, because in either case, it ends up not mattering because the memory is going to get released if you're following all this scope rules.
Yeah. So it matters a great deal. The reason being is for what we talked about before, where you're allowed to have as many immutable borrows at once and only one mutable borrow at once. That's very important. So you should always, always, always use an immutable borrow if you can, because that is the more flexible. It's basically like use immutable borrows. If that's not good enough, use mutable borrows, and if that's not good enough, pass ownership. And once you get used to the idea of ownership, like there are some really awesome things that fall out of that give you ways to design APIs that encode certain certain invariants or certain things that you want to be true, where in other languages you would just write a comment and say, this is the right way to write it. Like if you do this after this, you know, that's illegal, like don't do it. In Rust, you can enforce that at compile time, which is really cool. You can basically like encode in the type system the steps that thing has to happen in by using things like, okay, this thing will take ownership so that I know afterwards I can no longer use that thing anymore, right? Too advanced for today, but we can take a look at that at some point. Hannah, is everything okay? I think we lost her.
Yeah.
All right. No worries. Sorry, I didn't mean to call you out.
No, I was listening. I just had my headphones on the floor because I'm listening through the speakers.
Okay. No worries. Okay. Sugute, everything good? Cool. Cool. Now we can get to the point to actually implement our thing so that it's not hard, you know, doing nothing when we insert an hardcoding 0 when we call get. So, you know, this is a little bit also about how hash maps work, which is fun if you've never implemented one before. So the first thing we're going to do is a naive implementation, where it's not actually a hash map, it's just a vector or an array in disguise. And we're going to call it like buckets, and for a reason that will become very clear in the future. And we're just going to have a vector, and vectors, by the way, are just growable arrays. So like in JavaScript, for instance, when you call an array, you can grow, you can push more things onto it, and get bigger and bigger and bigger. In Rust, there are arrays, but they're fixed size. Yeah, they're always the same size. Vectors are growable. So we're going to have a vector, and it's going to hold on to our keys and values. And we're going to do this as a tuple or tuple, or a pair, depending on which language you're coming from and how you like to pronounce things. I call them tuples. Sorry if that's not how you pronounce them. So tuples are just they're pairs. They're, you know, two values that are kind of grouped together. And the first value is going to be our key, and the second value is going to be our value. When we set our keys are U64s, and our values are I8s, like that. What is it complaining about? I put it in the wrong space. Sorry. We got to declare it here, where we're declaring our types. Oops. Cool. So we're saying here we have a struct RMap. It has a field called buckets, and that field is a vector of tuples of U64s to and I8s. Does that make sense? And we get a complaint because it's saying, hey, like if you've used C before, if you use Go before, you don't have to initialize everything when you create a struct. Like everything has kind of a default initializer. I was very glad to find out that Rust does not have that feature. I find that incredibly confusing when I write Go, for instance. If you don't find it confusing, sorry, you have to write everything out. Yeah, you have to initialize everything. A little bit more verbose, but arguably much more straightforward. So we're going to say buckets is vec new, and vec new just basically creates a new vector. If you are, so there's something we should talk about real quick that I think some people might have a better grasp of than others, and that is the difference between the stack and the heap. If you've used JavaScript a bunch before, for instance, like you don't have to care about the stack and heap really, right? Like because almost everything in JavaScript is allocated on. You basically, when you declare a variable, it puts it somewhere in memory, and the garbage collector is in charge of it, right? In more lower level languages, for instance, even in Swift or, but also C++ and C, like the difference between the stack and the heap is very important. I won't go super into detail what the difference is, but it's something you should look into. In short, basically, variables that are kind of temporary variables and functions, for instance, are normally allocated on the stack. If you need something that lives longer than that, you don't know, like it might grow over time or change over time, you need to put it on the heap. And so vectors, for instance, they're things because they can grow over time. All of their contents live on the heap. But the vector itself lives on the stack. So that's the thing to kind of wrap your head around. When you're thinking about arrays in JavaScript, for instance, you just think about that array, right? Like it just lives there, right? And it doesn't matter if it could be a billion things long. Like you don't think about where those billion things are living. It's just there. And in Rust, you kind of have to care, right? You have a vector, which is just a struct, just like we could, we're defining a hash map. We could also, define a vector, and it's also a struct, and it holds on to a few things. But the contents of that vector live on it. So inside of that vector, there's probably going to be a pointer to where its contents live on the heap. But the vector itself is just going to be living on the stack.
What happens if the vector goes away from the stack?
If the vector goes, so here's a good use case for the borrow checker, right? The vector owns the contents, right? So when it goes out of scope, the contents can, like, it owns it. So if it's passed out references, immutable references or whatever, those all are verified to be, have gone away or whatever by the time that it goes out of the scope. So that's exactly like a great use case for the borrow checker there. It is impossible for something to be referencing those contents if the vector has gone out of scope.
All right.
That's impossible to do. Vector new, for instance, here, like, doesn't actually allocate on the heap. It waits until you push the first thing onto it before it allocates anything on the heap.
What's the comma at the end of the line?
Sorry, yeah. It puts a comma there. Like, I have an automatic formatter here. It's called Rust format, and it formats things automatically. You don't, like this, like if I were able to save it without it doing it, it would compile fine. The reason it does that is it's idiomatic to put a comma there so that when you put the next thing, you don't have to put a comma, that's all. Cool. So we got an empty vector here. We can continue to run this thing and it won't work. Like it's still it compiles, but it will crash and say like, hey, our value is still 0. So when we insert into our map now, we're probably going to have to insert into the buckets, right? So this should be pretty straightforward. Like we can call buckets, push. Sorry, got to do self.buckets.push, and then we can do key and value. And of course, we have double parentheses here because the first parentheses are for the function call, and the second parentheses are for creating the tuple. Any questions about that? Now,
for this function, the vector owns key and the value as well.
Yeah, and you can see that here, like we're taking this U64 by we're moving it into this, right? We could have just as much said this, but this will, and this will complain and say, hey, I'm requiring taking ownership over that key, but you're giving me a reference instead. I need ownership, which is exactly what this says here. Or it says, you gave me a reference and I needed not a reference. Which, I mean, this makes sense, right? Like the hash map should have ownership over the thing, because if it didn't have ownership over it, let's say something else had ownership over, you know, a value inside of there, and that thing went out of scope and the value was deallocated. Now you've got this like junk value inside of your hash map. That would not be good. Cool. So that's pretty straightforward. And again, it still runs and it will still fail because we're hard coding 0, right? But now it should be pretty straightforward to find the value for a given key. And what we basically have to do is loop through, look at all the keys, make sure that the key, like, is the current key that we're looking at equal to the key that's been passed in? If it is, return the value, otherwise don't. And then if we don't find it, well, we'll figure that out. What happens then, right? Cool. So let's go ahead and just do like a simple for loop. There's no for var I equals 0, you know, I less than 10, I plus plus kind of construct. It's a for n construct. And there's actually a lot of different ways we can do this, and we'll look at some of them because some are more idiomatic than others. This is the kind of most imperative way to do it is like this, where we say for pair in self dot buckets, and this won't compile, but we'll see in a second why. So for pair in self dot buckets, if pair dot 0 equals key, we can return pair dot 1. And we're going to keep looping. And down here at the end, if we haven't found it, then I guess we'll return 0 for now. I don't know. Like, we'll figure that out in a minute. And here we go. So it's complaining a little bit and says, hey, you can't move out of borrowed content. So when we call self.buckets, what we're saying is, give me buckets and give the buckets to me, and I now am the owner. But we can't do that because self right here is borrowed, right? I can't give you a book and then you tear out one of the pages and say, well, I own this page now. Can't do that. So instead we have to say, no, really, we just want to borrow buckets. Like we don't want ownership over the buckets inside. So we can do it like this. And yeah, it's looking pretty good. See, yeah. So our thing is compiling, it's running, and it works. That's awesome. Any questions about this?
Well, I just want to know, give her that 0.
Yeah.
Optional type.
Always. He loves the optional types. Yeah. So that's exactly what I wanted to talk about next. Exactly what I want to talk about next. It's kind of weird to return 0 if we don't find a key, right? Like what if the key's value is 0? Like how do we tell the difference, right? And I know everybody in this room is using their fancy new languages like Swift and Kotlin, and we all have our optional types. And yeah, Rust is a fancy new language too, and it has an optional type too. So we can doesn't have quite as nice of a syntax for it as Swift does. Or kind of automatic handling that Swift and Kotlin have for it. But it's a bit more explicit. So you have options. So now we're saying we're returning an optional I8, meaning we either return the value or we don't return it at all. And like I said, it's not exactly explicit or implicit like it is in Swift or Kotlin. You have to say, okay, if we found it, we found some value right here. You got to wrap it in some. And if you didn't find any, you say, hey, we found none, like that.
Okay, that's pretty much like Swift, just Swift hides behind.
Yeah,
the now.
Exactly. It's exactly like Swift without the syntactic sugar that Swift gives you. And in fact, we could, we haven't gone through enums, but like it is an enum.
And we have to mark the assert value as some too, right?
Yeah, exactly. So now we're getting an error up here and saying, hey, I expected an option, but you gave me some integer. What are you doing there, buddy? And so we got to say, no, we actually expected this thing to be some too.
Awesome.
And if we want to unwrap the sum,
Yeah, if you want to unwrap the sum, there is an unwrap. So for instance, we could go back to this and say unwrap like that. And if it's none, unwrap will panic. And what panic does is panics are like exceptions, except you can't recover from them with an asterisk. So
okay, it's just
yeah, the whole thing crashes. Panics are, we will get to error handling at some point, but a preview is basically, in Rust, there are two types of errors. One is a fatal error where you cannot recover from it. And in that case, you use a panic. So for instance, when we say unwrap, what we mean is we know for a fact, like we're smarter than you, compiler. This thing is there.
Is there something like try and catch?
There's not a try and catch, no.
Okay.
For errors that are recoverable, you have something called a result type, which is
Okay.
just like option, except instead of some and none, it's either the value or an error.
Yeah.
And there's some syntactic sugar to help you out with that, but there's no try catch. Something like that is kind of eventually coming to Rust, but it will be just syntactic sugar around that, and so there's not going to be exceptions in
All
there.
right.
Another thing you can do here instead of unwrap is expect, and expect then takes a string. It's like I really thought this was not none. Sorry. So you can do that instead.
and what would that
Same thing as it's the same thing as unwrap, except you get a nice printed error message that says what you put there, basically. I would say almost always use expect, which is nicer because then you get a nice better error message. Only use expect if you like absolutely are for sure that this thing is going to be there, or it's early on and you're like, I don't want to deal with errors right now, let me just do this. But when you're actually running a real program, you want to try and avoid unwrapping as much as possible, because of course it's a panic, like you cannot recover from it. Then we can do like assert value 2 is none here, because we're getting map.get 5. Cool. So that's nice. There is one more way to write this, a way that some might argue is a bit more idiomatic. We're gonna change it up for all the functional programmers in here. I love their functional programming. So me. So now we're going to do self.buckets.find. This is going to give us a pair. We're going to say pair.0 equals key. So this will find the first pair in our vector of pairs where pair.0 equals the key that we've passed in. And then that gives us that pair So then we're going to map for that, because it gives it an optional pair. We're going to map over that, get the pair, pair.1 to get the value out. And we get this thing called no method named find for vector. That's because that's true. We actually want to get an iterator over the vector.
Before you talk about what the fucking iterator is,
Yeah.
Can you just structure pair? Can you just structure it inside of the pipes?
Yeah, you can. There's a caveat to that we'll see with the error message that we get. So you can say, well, let's give it another name, like maybe K and V. Here. So this will almost work. It's saying there's no implementation for reference of U64 to 64 because K right here is a reference to it. The reason being is when you're iterating over the thing, it's not giving you ownership over the value, because then once this find would go out of scope, it would basically just it would deallocate that number, and so you would no longer be able to use it.
But if you do, can you do the C thing if you do a star pointer, like a star like
Yeah.
that, and you reference it?
Yeah, so you can do this. Now, the reason that you can do this is because it's a U64 and because it implements a trait called copy. We'll talk about that in just a second.
But the thing that I don't understand about that is that is the reference to it. Well, okay, wait, so it is a reference. So the K before without the star was a reference inside of that scope, and it lives inside of that scope. But like, and okay, so if it's a integer, that's copyable by, that's very easily copyable. But if it was a more complex type, like a custom type that you created, and you wanted to test for equality, would you have to do the equality? Would you have to define an equality function for a reference and then also for the value type itself, or
You would just do this. You would just take a reference to the thing.
That makes sense. Yeah. Okay.
So we can like, the reason I wrote it as pair was to avoid talking about copy, but I think it's something that we should talk about relatively soon. There is one additional caveat to our borrowing thing that we should talk about that gets us around some of this stuff. But like, we'll finish this up and then we'll talk about that because it's actually interesting and a good thing to know. Warning here around V, because it's not used, we can just call it underscore. We can do the same thing here. We could say underscore V and return star V. So we have to dereference it because V again is a reference. So we had to call self.buckets.iter on this because we need something that allows us to keep track of how we're iterating through. There has to be some value that is basically keeping track of where we currently are in the loop and stuff like that. And the vector doesn't have any of that bookkeeping associated with it. Yeah. We have to get some value that basically like holds up, like has reference to the vector and then has like, current index or something like that. We don't have to look at how it's actually implemented, but there's some kind of bookkeeping associating with iteration, and .iter gives you that like bookkeeping structure to be able to do that.
Is .iter defined part of, and this is like a code level language defining question? Is that defined on the vector itself, or is it a trait on the vector?
I believe .iter is defined on on the vector itself, but then find and map are all implemented on a trait called iterator, basically. So iter right here returns something that implements this iterator trait. That we can do fancy things like find and map and flat map and all the things that you're probably already familiar with from functional style programming. And the kind of awesome thing about this is like it compiles down to basically this up here. And in a lot of cases, the compiler can even optimize it further than it can optimize this. And so if you want to write fast code, a lot of times this ends up being the faster variant. For the most part, though, it's kind of preference. Like for this particular use case, I find this find map to be more clear about what's going on. I find the key and then I map over it to get the value. That's kind of how I would describe this anyway. But of course, there are some times where like the more imperative way of doing things is clearer, and in that case, you can just pick the imperative way of doing it. Cool. Any questions? So we're going to talk about copy real quick, which is something I didn't talk, like the last time I gave this little workshop, I didn't talk about copy, but I think it's interesting because it's a wrinkle in how the borrow checker works. So we saw this before where we could do, and we actually are still doing it for value. So right here, V is a, and you can ignore the single quote empty for now. The ampersand, it is a reference to an I8. So this V is not an I8 itself, it is a reference, it's a pointer to it. It is pointing into buckets. So that the value is still like, the bucket still owns it, it's still living inside of the buckets. And what map, the function, the lambda that we pass in the map, what it gets is just a pointer up into self.buckets, right? And this makes sense, right? Like we don't want, if we passed ownership into find or into map, they would have ownership, and once V went out of scope, it would be destroyed basically, and then you have invalid memory inside of self.buckets, right? So the question becomes, and the thing that really, like, if you understand the borrow checker really deeply, as we have seen it so far, this should not be possible, what we're doing right here. We are dereferencing the value, getting ownership over the value, and now we have ownership right here. We're passing ownership out. So and in fact, right here, it's the same thing. We're calling pair.1, getting ownership of the value from the pair, and then passing it out. So now, if we didn't copy this value, then the value would be living inside of our option I8, and it would be living inside of self.buckets. It would be in two places, and we can't have two owners of things, right? We need to have, like, this makes, if you really think about it, it doesn't make any sense what's happening. Like, we now effectively have two owners of that value in there. And there's a reason why this is, and that's because these numbers implement a trait called copy. And what that means is, instead of moving things by default, like when I pass in this key here, instead of moving the U64, or like passing ownership into insert, instead of doing it, copy the value instead. So you can see here, like, let's do let value equals 10, right? And values, maybe this value 2 now is, let's do it up here. So we're going to say let value equals 10, and we're going to say map dot insert, and our key is going to be 10, and our value is going to be, well, let's not do 10 here, let's do 90, and our value is going to be 10 as well. Right? Our value is going to be this value thing. And then we're going to do the same thing, you know, here. And according to our borrow rules and our ownership rules that we've talked about, this should not be possible, right? Value has ownership over this memory, over 10. We pass in value into assert by ownership, right? It's not taking a reference. It's saying, hey, I want ownership here. And then we do the same thing on the next line. And if you remember what we said before, you can't do that. If I give Peter ownership of the book, I can't just turn around and give Sigute ownership.
If copy will be implemented on numbers, then in this case, the compiler will enter an error saying that borrow exception.
Yeah, exactly. And if, in fact, let's do that real quick with Vec. You know, we'll say this value is going to be, we're going to use the regular collections, which is generic and allows you to use any key value. We'll talk about how to implement that in a minute. So we're going to use our, the regular, not our hash map, but just map. And we're going to say, map is a hash map. And our value is going to be some vector of, I don't know, U8s, unsigned 8-bit editors, right? And then we're going to try and pass in, let's get rid of all this stuff here. And here we get the error that we expect. And best of all, we got the error saying value was moved on line 6. Then we tried to use the move. We've seen this before, right? This makes sense to us, right? But look what it says right here. Move occurs because value has type vec of U8, which does not implement the copy trait. And that's the key right there.
So any type that implements the copy trait is passed by value.
And the better way to think about it is, by default, variables are move. You move variables in function unless a type implements copy, in which case you copy them. And if you're used to C++, modern C++, you talked about move semantics versus copy semantics. C++ is copy by default, where by default, when you pass things into a function, it copies the thing. In Rust, it's move by default. You move things into a function unless it implements this copy trait. And you should be thinking to yourself, okay, well, why does vector implement copy? And doesn't implement copy, but numbers do. Why is that? Well, that's because copying numbers is super cheap. It's just a number. Like, that's what computers do, right? They just copying 7 from one register to another is like one cycle of the CPU. A vector has all this machinery associated with it. It's got things on the heap that it would have to copy, it would be mayhem, right? It would be very, very expensive to do that. And so by default, we're not going to do that. There's a way to copy a value explicitly. It's called cloning to differentiate between the two. So you can explicitly say here value.clone, and actually you would have to do it up above first. So we're going to clone it right here, and that means that the thing that was passed out from cloning, it literally took the vector struct, it took all the things that were on the heap. In this case, there are none, but if there were, it would copy all those values, move them to another place on the heap. This whole orchestration of things, and it would pass that into assert. It would move that into assert, but our value right here is still owned inside of this function, so it can be used again. And then we pass it into map assert right here, and now after that we can no longer use value. This is been moved, right? So the important thing to remember here is that you pass when you see this syntax here, where you don't see an ampersand or an ampersand, but this thing is being moved into the function unless the type is copied. in which there is only, on numbers, booleans, what's that?
Individual chars or everything back by.
Individual chars or, yeah, like individual chars and stuff like that. Things like that, those are copied. And you can, derive copy for your own types that, your structs and stuff like that. But you can only do that if all the things inside of it implement copy, right? And you should really only do that if it's very simple struct. And clone here is what you should use if you want to, because you want the user of that type to know, okay, I am explicitly copying this thing. And I am aware of the cost that cloning has. Okay. And for a vector, especially for an empty vector, it's very small cost. If this thing had 100,000 things inside of it, it would be a huge cost. And so you probably should not do that.
Even an empty vector, right? I see that in the documentation, you can initialize it with its capacity, whatever capacity you want. And so even a vector that has no values in it might,
yeah. If you use vec new, it doesn't allocate on the heap. So in this case, it wouldn't be, but it might be. If you don't know where this vector is from, you should be very cautious on clone, right? So that's what allows this to work right here. If our value was a string or a vector or something like that, we would get a borrow checker error here saying, hey, you are trying to move out of borrowed content. Value right here is borrowed, and you're trying to get ownership of it. You can't do that, buddy. This thing's not cloned, or it's not copied. And if you understand that, you are like on week 5 of Rust already. So congratulations. Any questions? I know that's kind of confusing. Any questions? I didn't hear anything from you.
No, looks on it.
Okay. Hannah, are you doing okay? You don't have to answer.
I was just wondering about the copy thing. Is that just like a flag that you add to your declaration, or is it something you have to implement?
Yeah. So let's say we wanted to, like, our map is not something we want to do copy on, but let's say we had a struct, our struct. And let's say, it's got, age is U16 and weight is U16. These are 2 numbers. We should be able to copy these things. It's fine if this thing is one's copy. It's just going to copy 2 numbers instead of 1. That's acceptable. So what you can do here, and this is kind of a new piece of syntax, is derive copy. And what derive copy does is wrong brackets here. It will just automatically figure out how to implement, what is it complaining about? Oh, and in order to implement copy, you have to also implement clone. You can't have copy without cloning, which makes sense, right? Like, you should be able to explicitly copy, implicitly copy if you can explicitly copy, right? So you have to do them both together. And this will work. And this is just shorthand. If we go into the docs for copy here, copy is not really special. It's just included in the standard library. And it has that one extra thing of the compiler doing it, copying instead of moving. You can see here's the deriving. They're also deriving debug for being able to print stuff out. But here is how you implement it. So, impl clone, that's, you just got to implement the clone function here. That's fine. Whatever that means for your type. And then copy is it's what's called a marker trait, but there's no functions on it actually. It's just, you just mark it and say this thing is copied. And this right here is equivalent to this. So obviously this is shorter and this is what you normally do. You can also create your own derives and stuff like that for your own traits. We haven't talked about traits and stuff like that yet, but We'll get there.
I want to take it back quick.
Yeah, let's do that. We'll take a 5 to 10 minute break. We'll be back. Cool. So now we've got it working. It's not really a hash map because it's just a vector that we have put some fancy stuff around. So we have to look into actually hashing, which is what gives hash map its name. So the way that hash maps work basically is you get a key, you hash it, and then you get some number out, and then that number tells you where inside of your vector of buckets that you put your key value pair, so that when you're looking it up again, when you're in the get method, basically what you can do is rehash that key, get to the bucket, and go straight to it, so you don't have to iterate through the entire vector of buckets that you have. So that's something that we probably want to do. So if we're looking, how to hash things, we should kind of maybe search for hash here. Let's see, we've got hash right here, which is a trait where we can hash things. That's good. We don't really want to do that directly. We have also standard hasher right here. This is great. It's even showing us right here how we can go ahead and hash things like that. Basically, what we want to do is get a hasher, and we're going to use here. I think it's here. Hash. No.
Not default.
Yeah.
Hash, not default hash.
Yeah. So default hasher we can look up and see what it does for us. So basically, it implements hasher, so the trait for actually doing hashing. The reason we can't use hasher directly is because it's a trait, and traits are just interfaces. They're not actual concrete types. So we need some default hasher. We can use this one here. It's maybe not the fastest one, but it's generally pretty secure. So that should work fine. So what we can say then is let hasher equals default hasher. By the way, I didn't really specify it up here. This is how you import things. Use and then kind of the name spacing into it, and then you're able to use it like that. So we have a hasher, and then if we go back here, I don't think it has the exact example of what we want to do here. No, but I think what we need to do is take our key and call hash on it. And I think we need, Anthony, since you just wrote this, you can correct me if I'm wrong here. We need standard hash.
It's like hash and hasher, I think.
Yeah. Hash and hasher. So you can see here that hash is a trait that makes something hashable. And then hasher is the trait for actually doing the hashing. And then we pass in here. So this is just the way hashing works, where we take our key, whatever it is, we call the hash function on it. This hash function is oops. This hash function is defined by this hash trait here. Oops, what is it saying? It's saying that it's not mutable. We gotta say that it's mutable here. I don't know if we need hasher, but because it's telling us we don't use it. But anyway,
You have to finish it. So I think
that's
that's
true.
it's not telling you that I'm not.
So this kind of hashes the key on the hasher, and then we get our index back. Or so this should work. Yeah, should work. I guess it is using it now. So this is how hashing works. We get a hasher. We call hash on our key, passing in that hasher. And then we call finish on the hasher, and it gives us back some number. So it has basically turned our key, which is already a number, turns our key into a number. But you can imagine our key being a vector or a string or something like that, where it needs to turn it into a number. And what we're going to use that number to find the index at which we put our key value into. So that later on we do the same process again, and then we can go straight into that index. The problem, of course, is that this number is a U64, so it might give us a number between 0 and some trillions of, quadrillion, whatever the maximum U64 is, and our buckets presumably are not going to be that big. We don't even really have enough memory on the machine to hold all of that, so that's probably not the right thing to do. What we're going to want to do instead is call modulo on self.buckets.len. So this constrains our number to be between 0 and whatever the length of our buckets is, so that we know for a fact that when we push this thing when we put it into our vector, it's at the right space. Okay, we're getting complete here because len is actually a U size. We haven't talked about U size. What U size is unlike a U8 or a U64 or a U32, which are known numbers of bits. U size depends on the type of machine you're on. So it's also known as like a pointer size, a word size, things like that. So if I'm on a 64-bit machine here, it's going to be 64 bits. If you're on a 32-bit machine, or if you're super old school and following along on a Commodore 64 or something like that, it could be as small as 8 bits or 16 bits. Cool. So in order to get around that, we're going to have to just say, okay, treat this U size as a U64. And what that does is, on my machine, this will do basically nothing because I'm already on a 64-bit machine. Oh yeah, sorry. The syntax for multiple imports is just a curly brace and and in fact, we could actually do it like this. We can do hash. We can nest as far as we want to. That should work as well. Yeah, cool. So if we were on a 32-bit machine, for instance, this as U64 would basically just pad the number with zeros at the beginning. So now, what we would expect to be able to do is like self.buckets, okay, this is our index. And then we're going to pass in our key and our value like this. So we found the index at which to put it at, and we're going to put it there. And this is, familiar syntax for everybody. It's complaining here now and saying you can't index into something with a U64. You have to index into it with a U size. So actually, I'm going to change what I did before. Instead of changing the length to be a U64, well, no, let's do that. Do U64 here, and then we'll just say, okay, now treat that U64 as a U size. So it can be a bit annoying, right? Having to be explicit about what numbers you want to treat things as. The nice thing about it is, unlike in C or C++, like it gets very old very quickly, not knowing what the behavior of numbers is, when you're going to truncate numbers, things like that. And so this makes it very explicit. And these as conversions are only for conversions that are unfailable. Like they will not truncate the value or something like that. So they could truncate it, but they won't fail. There are also like intos and stuff like that that can help there, but we'll get into that now. So does this make sense to everybody? I know the hashing is a bit
Yeah,
weird.
this all makes sense. Did you change the definition of buckets and structs?
No, I did not, or I don't think so.
No.
You're getting an error?
No, I was just thinking this.
Yeah, sometimes it's slow. Yeah. That is definitely the biggest pain point of using VS Code. It's the RLS is pretty slow, and we're on a small code base here. So this implementation does not work. Does anybody that's not Anthony know why? And I'll give you a clue. It does not work because of this right here.
This one.
This right here, the self dot
Yeah, I
button.
mean, it's a whole line doesn't make sense. Because like you're setting a tuple for integer value, I think would be fine. Yeah, I find this.
I think
Or are
that,
we just reaching into the indexing entirely?
that part's
Okay,
correct.
yeah,
Like
I see.
we're getting the vector, we're indexing into that vector, and then we're placing the key and value tuple at that index, right?
Okay, so then
So-
buckets is not initialized in any way, right? Like we haven't pushed anything onto it, so it doesn't exist.
Yeah. So that's correct. Like in a lot of languages, JavaScript being one of them, for instance, if you have an array, no matter what you index into, you can always, like you can index as far as you want to, right? Like you create an array and you say, okay, the 7 billionth element in this array is 4, it's fine with that, right? That is not how vectors work in Rust. Instead, what you have to do is you start out with a vector that has nothing in it, and you can push things onto it, and it can grow with that, and you can index into that vector in any place inside of that length. But if you try to access memory outside of that length, it will panic because you're accessing uninitialized memory. If you're used to C, it should make sense, except in C, you just get back garbage. Whatever happens to be in memory at that point, you would get an integer. Yeah, you will get an integer. In Rust, there is bounds checking. So at runtime, it will check, is this thing within the bounds of this vector? And if it's not, it will panic. There are ways to get around that if you really, really need to. You index into vectors and arrays in Rust a whole heck of a lot less than you do in C because of iteration. This stuff tends to get you around having to explicitly index into things. Bless you. But if you ever find yourself really, really, really needing to get rid of balance checks and you're very, very, very sure that you're reaching into valid memory, there are unsafe ways to get around that. But that's neither here nor there. We'll talk about that at a future session.
So, just a quick question. Right now, the way that's set up, the vector has a length of 0. So the index currently is always 0. But I guess when we run this, it will panic or will it actually work? Because
So
starting with 0.
yeah, so it will panic. The reason is because you want to index into the vector at index 0, but it has no indices in it at all.
Not actually.
Yeah. So it will panic. In fact, maybe we can run it. And the first, we actually don't even reach that far. We get a panic here saying attempt to calculate the remainder with the divisor of 0, because right here we're length is 0, right? But we can also say, let's imagine that just returns 0, right? this will also vanish. I gotta comment out the line. Index out of bounds. The len is 0, but the index is 0. So length has to be at least one more than the index, right? Cool. So, in order to fix this, we have to change the way we model things a little bit, because one thing we could do, right, is just at the beginning here, push on tuples where the key is 0 and the value is 0, but that's sort of similar to what we talked about down here, where like 0 being the special value is kind of weird. What happens if the key is actually 0, or the key and value are 0? How do you distinguish that between an empty thing and stuff? But you know, our old friend option is here to help with us there. So what we can basically say is our buckets are now a vector of optional tuples, and what this allows us to say is if that's set to none, then we know it just hasn't been initialized with anything. Right. And we need to come up with an idea of, well, how many buckets should we have and stuff like that. We want to initialize it. Eventually, every hash map implementation has a way to grow the number of buckets that it has and stuff. I don't think we'll be able to get there today, but we should start with some initial number of buckets that we can pick out of thin air. And probably we would change it with testing and say, well, 4 is a good default, 8 is a good default, 128 is a good default, who knows? So for now, we can say const initial bucket size, and constants in Rust are with the const keyword, and they're usually, by convention, capitalized. We'll say this is the U size, and we'll say, what's a good one?
5,381.
5,381, because Anthony says so.
I see that as a const that people use when doing hashes.
So it must mean something.
It means something.
That's good. That's good.
It's probably a prime number. Oh.
Okay, so now we're gonna say let buckets. We're gonna do our thing here where we say, okay, buckets is we'll do a new vector here, and we can go ahead and let's do something fancy here. Let's do for underscore and 0 to initial bucket size. This right here, if we do this is range syntax because it's a range between numbers and it's an exclusive range. So how we have here is 0 to 530 and unto 5,381 exclusively. So it will be 0 to 5,380 inclusively, which is in total 5,381 buckets. And then we're going to do buckets dot push, and we're going to push in none like this. And then here we have a nice syntax where we can just do buckets instead of doing buckets colon buckets. We can just do buckets here. I think JavaScript also has this, where if you have a struct that has a struct's field's name is the same as a variable that you have, you can just skip writing it the second time. Instead of buckets colon buckets, you can just do buckets.
My 2012 number.
Cool. Yeah, let's finish this up real quick. We're getting a complaint down here because this is not an optional, so we just need to wrap this in a sum. That's pretty straightforward to fix. We'll fix this in a second down here. One interesting thing to note here is this, we have a performance issue here that we can get around pretty easily. And the performance issue is the fact that we initialize this bucket, and for every item, we're pushing that item onto the bucket. And a vector, a vector needs to keep control of its heap allocation, needs control of the things that it has inside of it. And initially, when you create a vector with vector.new, it creates a vector with 0 length and nothing on the heap. It hasn't called malloc at all. There's nothing on the heap associated with it. When you push the first item, it allocates something on the heap. And if you're familiar with heap allocations, you know that you shouldn't just like take exactly the amount that you allocate on the heap. Should, especially for growable things, you should probably be a bit greedy and allocate a bit more. So what vector does is maybe it allocates enough for, I don't know, 124 bytes or something like that. And then figures out, you know, after you've pushed 3 or 4 on it, wait, this is not enough, I need to allocate more. And then you push on even more, and it's like, oh gosh, this isn't enough either, I'm gonna allocate more. And so by the time we finish allocating here, we probably will have called malloc or some, we will have initialized memory on the heap several times. Not sure how many, but several times. And that's not good. It would be nice if we could just do it all at once, allocate a big chunk on the heap, that's enough memory there, and once it's a, you know, and then push it on, and it's all pretty cheap then. We can't do that, really. So vector, we know, has a length associated with it, probably has a pointer pointing up to the heap, and it has one last thing, it has a capacity, and the capacity is the amount of space on the heap that it has allocated for itself. So if we call something like vector with capacity, and that just expects how many things of type T that we're expecting to push on there. So you don't have to do any, you know, any math to figure out how many bytes or anything like that. Just give it how many things it's going to have on there. And then it will go ahead, and when it allocates onto the heap, it will allocate as much as it needs for all of those things. And so here now we're only allocating on the heap once, strictly once. Does that make sense?
Is there something like, I thought there was something that was like with exact capacity, or?
Yeah, let's take a look at that. Take a look at exact capacity.
With capacity, try reserve exact. I see as reserve exact. Maybe capacity does exactly that. Like, oh yeah,
Capacity
does exactly capacity.
Yeah. Capacity is for our use case the right thing to do because it gets exactly what we needed to have. But yeah, this like reserve exact and stuff like that, these are all like reserves the minimum capacity for exactly additional more elements. So this is, you know, this is a, you know, before this is creating a new vector, whereas this one right here is getting more space on an existing vector, for instance. And there, you know, there are different things for doing that. They also have these like try reserve, like for still on Rust allocation, you cannot recover from allocation errors. So like, let's say you run out of memory, it will panic Rust, which for a Mac and for Windows, you know, for normal programming, it's fine. That's a fine default, and you should panic. Like, there's nothing you can really do there. If you're writing an operating system, or if you're writing for embedded devices, small embedded devices, you probably want to be able to recover from allocation errors. A lot of times you just run out of memory and you need to do something based on that. And so they're coming out with different APIs for basically handling that instead. So cool. So we got one more issue to get through now, and that's basically we have the ability now to insert into our buckets, but now we need to get them out of the buckets. So I'm going to go ahead and copy this. Oh, we probably should refactor at some point. and just say, we can just take this down here for getting our index. Just say, I don't know, fn get index for key, something like that. The key, and our key was what, a U64. It's going to give us back a U size. And we're just refactoring here, moving some code around. That's cool. We want this to be a method, so we can have access to our buckets there. This is great. Now we have refactored that, and this is a bit shorter now. Index equals self dot get index for key, where we can pass in our key. Awesome. We don't have to cast this anymore. So that's good. We're back to where we started, but now we can easily get our index again. So let's do that. Let get index equals index for key. Pass in the key. And then we can call self.buckets.get, and indexing, with square brackets. If it's outside of the length of a vector, it will panic, like we said. But get does the bounce checking as well, but returns an option instead of panicking. So it's usually preferable to do this way, unless you're like really, really sure. We can call that instead of index, and that should just work. We're going to call self here. Oops. Of course. So we're calling self.buckets.get on index, and we're getting back our key value pairs, right? So we don't want that, but we can do the same thing we did before, which is just map over them and just say key value. And oops, and I forgot to close this. So we're mapping over our key value pair and just taking out the value. Oh, of course. We need to now have options in here. So this is a good question to do here, right? We get it back an optional right here, and then we need to, if that thing is sum, we need to then go in there and extract out or look at the value again and see, is it sum again? So we kind of have multiple versions here, right? Where we have an option on the outside from the call to get. We have option on the inside because our values are actually options. So we would like to flatten that down. If you look at the documentation for option, there is something very nice that exists on option to do this. And it is called and then. Here it is. So returns none if option is none, otherwise calls f, the function with the wrap value, and returns the result. So you can see here, it expects a function from t, the inner t inside of our option, and to some other option, and kind of compacts it down. So we can do something like this, where we say, and then then now we have access to our inner thing. What is component done here? there we go. We had to dereference our pair here because again, we're getting references into our buckets here. This relies on the fact that our key and value are both copy. Is something that in the future we might not be able to rely on, so we might have to refactor. But for now, we can rely on that. We can dereference it, and instead of it moving the value out from self.buckets, we copy it because a pair of two copy values is also copyable. And it's complaining buckets here as invisible, which is true. We need to change that, and then now I think we should be good to go. Cool. So this is great. If we run it, I think it will pass. Yep, it does. Yeah. Yeah. So again, just to explain this and then, basically we're getting right here, P, we can see is a reference to an option. So it's referencing the option that's sitting in self.buckets. And we're going to dereference it and say, well, I want this thing. And if this thing weren't, if the tuple of U64 and I8 weren't copied, then it would complain here and say, hey, you're trying to get ownership of this thing. And this thing is owned by self.buckets, which you're borrowing. You can't do that. But luckily our pair is copyable, so it just copies for us.
I mean, in practice, what we want to be the key, we want to be a reference pretty much everywhere except for the point in time when we're putting it into the tuple.
Yeah.
Right, like, and then we would be calling clone ourselves, right?
Yeah. We probably don't want to make it, we probably want to leave it like this, where we have to take ownership on insert. Because then we would have to require that key and value are cloned, which you may not want to do, right? So you want to take this by ownership, and then everywhere else, we're kind of getting a little bit ahead of ourselves, but I think we've got 15 minutes left, so maybe it's the right thing to do. We do have a massive bug in this right now.
Here we go.
Yeah, it's super efficient and super, there's a massive bug. For those watching at home, the massive bug is this call to get index for key might return the same usize here. When you hash something, there is a possibility for conflicts. That's true by itself, right? Like, you might hash two different things and they might actually hash to the same thing. Like, there's no guarantee that your hash will be globally unique, but it's super unlikely. You have all of the 64-bit space to work in, and that's pretty unlikely. But I mean, our vector is only, what did we say, Anthony? 5,381. Like, if you got, 10,000 items in there, you have to have had conflicts before. So what we're doing right now when we insert something in here is we're just overriding the value.
So a bucket is really just a reference to get that part of the hashes easily, but that should be a vector itself.
Yeah.
And we have to go through and check it.
Yes. So the homework for the group then is to fix this by turning this into a vector of options. And what that allows us to do is quickly get to our little subsection of our buckets, and then we have to linearly search.
Yeah.
So it's sort of a combination of our second attempt with our first attempt. They're put together, and that actually is what will make our hash map, right? Get the index. There might be conflicts, so you're going to get to another vector there, and you're going to linearly search through the vector and match keys. But, presumably you will only have to search through a few items instead of the entire hash map. So it's going to be much more efficient that way. So we'll leave that up to you, the viewer.
Wrap it up to the vectors. The vector of vectors will be a vector of collisions.
Are you talking about what to name it or?
Well, no, I'm just trying to what
Yeah.
we're talking about.
Yeah, so basically you're hashing, you hash your key, right? And that gives you an index. Now, multiple keys might index to the same thing. So what you want to do is actually insert it into a vector so you can hold on to multiple things that all happen to have the same key. That's very unlikely with something with 5,000, you know, if we have 4 items in our map, they probably won't collide. But as soon as we have more than our
They
size,
don't have the same key. They have the same hash
Yes.
for the different keys.
Yeah. they have different keys that hash to the same thing and therefore give us the same.
Or they have the
I
same index of the bucket.
Yeah,
Yeah.
yeah, and it's not even the same hash, right? Because different hash, we're
Yeah,
modulating by the size of the
yeah,
vectors, so they probably will have different hashes. It's really, they just happen to be truncated down to the same index.
Especially if the indexes are integers, I'm pretty certain that the hash should be different. You would also.
Yeah. So yeah, we'll leave that up to you, the viewer. As far as like how we're modeling things, so I want to go over generics real quick, and then we'll do a little change to our API, and then I think we'll close for the day that way. So right now we're forcing the types of our map to be U64 for the key and I8 for the value, and that's obviously not that great, right? We want to be able to just say, give me any key and value as long as the capable of doing this, and that should be good enough. So we can go ahead and do that with using generics. So we can say that our map struct is generic on K and V for key and value. And then we can change our little buckets here to be K and V instead of the concrete types we had before. So right now, these are any types K and V. We have no guarantees about them. And now we need to go ahead and do this, where we say we're having an implementation for some generic types key K and V for our map of K and V, like this. And we got to fill in all these things, K and V.
What is the interesting point? So you have to do.
Yeah, this
You do that. So you implement and you say, this is, but what are you actually fucking saying there, right? Like,
So if you didn't have this, what Russ would understand is you're doing impl for our map for some type K that I should know about. And it's like, I don't know what K is. What is it?
Yeah.
And so in order to say, no, K is like generic, like,
Don't
you know,
worry about that.
yeah, then you have to say we're implementing it here.
okay, could you put concrete types then? Like in the leftmost one, could you do our actual types?
Yeah.
Okay.
Yeah, you can have, you can basically specialize your implementations for things and say, for instance, I want to, you know, our map, I want to have a method on our map when the value is strings. That will only exist when the value is strings and nowhere else.
Okay, so what I just did is, so if I did, so I did implementation and then getting rid of, exactly what you did, except I replaced the first K and the first V with U size and then I8. I didn't do anything for the second K and V, and now it tells me it doesn't know what the fuck K and V is.
Yeah.
So would I do U size and I8 and to replace both of the K and Vs?
No, what this is saying is there are some generic types we're calling K and V.
Okay.
We can say that these are instead U and Vu. And now we have to replace all these with Ku and Vu. So these are basically just, the first two are just setting up generic type names that we're going to call K and V. You might see U and T a bunch, you might see, yeah, whatever, A and B.
And so we have a problem on the index, because we actually have to restrict it to things that implement hash rate.
Yep.
Yeah.
Hashable, and then And presumably comparable.
Yeah. So let's change this real quick so we can take our K and our V. That's pretty easy. We're gonna have to change this as well to take our K like that. And then I think now we're basically only down to here, right?
Yeah.
To these two. Okay. So
It is fine, it's just the index.
yeah. So what's awesome is the compiler kind of tells us what to do. So it's saying no method named hash found on type K, right? But there is a candidate that has a hash that you might want to look into, and that is standard hash, right? Which I believe, yeah, we already have imported here. So all we have to do now is say K is hash.
And should we define that on the struct also, or?
So that's a good question. Like, should we define this also on the struct? And it's a little bit down to how you want to model things. I would say the thing that people normally do is constrain the implementation and not the struct definition itself. You can do that for the struct itself if you wanted to. We could very easily say K can only ever be hash here. I think the reason people don't do that is it's not really necessary. But for our purposes, like,
Yeah.
it will only ever be.
It's only actually necessary for the.
Yeah. And you have to write this anyway, right? Because if you didn't write this, and if we had done K here and our struct definition, K is hash, and we didn't include this part in our impl, it would say generic type K is not hash. And so we would have to write, no, generic type K is hash. And then it would so it would basically be just more work.
I'm trying to do both clone and hash. How do you do that? Do you do it with a pipe operator or with a plus? With a plus.
Yeah. So we got one more thing here.
Well, the vector says I can't.
So let's go through here since we can all see this this screen here. So we didn't change this, by the way. So this is fine. We're doing well now. This should compile now right
the
here.
Option should be K, right? Should be returning option K.
Yeah. So we can set our value.
V.
Yeah, V here. So this is good. Now we're finally going to get to what we talked about before. We're moving out of borrowed content right here, right? So we said this before. The only reason it worked before was because our pair implemented copy. And so when we tried to move out of the borrowed thing, it just copied for us instead of moving it. But now we have no guarantee. K and V can be any types, including types that are not copy. And so this is saying, hey, you can't do that. Self.buckets owns this thing. You can't just take it. You can't move it out of self.buckets. What are you doing? So you could, I think what Anthony was going down was like implementing, we could do hash plus clone, and V is clone now. And then here we could say p.clone like this. And there we go, that's working. So that's good, this works. Yeah, interesting. Yeah, we have one more issue here, right? We're taking get index for key, takes ownership over key, right? We didn't say this is a reference, so get index for key will get ownership over the key, and at the end of this, it will be destroyed, right? Which is not good because up here, like we want to use key, and then we want to like put key inside of our buckets, right? That's not good. So the fix for that is pretty simple. Does anybody have a fix for that? Mm-hmm. So we could have cloned it, but that's, because we know it's clone, right? But that's pretty heavy-handed. So this is a bit easier. We just make it here a reference instead, and now we've just got to pass this by reference. So this works fine. Okay, and we got to pass this by reference now. That's good. Now we should be good. Okay. Yeah, so that's the thing, is like, we probably shouldn't be cloning, right? I mean, that means we can't have things that are not cloned. We're forcing everybody that uses this thing to clone for their things. Can we not do that? That would be nice, right? And so let's get rid of that. So we can remove clone here. But there's no way to do it without changing our public API. So we're going to have to do that. We can no longer call clone here, right? So this isn't good. Okay, all right. We're getting a reference here. We don't want a reference. We try and dereference it, but that moves it out of self.buckets, which we're not allowed to do. And oh, okay, what are we going to do? Well, we could do this and just say, we're not returning ownership of the value anymore. We're returning a reference to it instead. Does that make sense?
Yeah.
So now get doesn't return ownership of that value. When you call get, you don't get ownership over it. You don't get a V. You get a reference to the V. And that reference is pointing into the buckets inside of the hash map.
So,
yeah. Here, what we have to do is, what we can do instead is just do this. Best. We can look at match syntax real quick as well. That's nice. So here we can do pattern matching and say, if it's some key value, turn the reference to the value, and it's none. And of course, here we got to do some of the.
it says that I'm being explicit lifetime.
Well, I think we'll get there in a second. That should be the last. Yeah. This is where things are a little icky here. There's a better way to refactor this, but we just don't have time to get into it. And this should work here. So now we're just pattern matching on self.buckets.get, and if we get a value and that value is a sum, then grab the value out of it, which is a reference, and then return that, and otherwise return none. We can change this also to. Does everybody understand how the ampersand here, like why we're doing this and what this reference is referencing into? It's referencing the memory inside of self.buckets. And so these two references are in a way kind of linked with each other. As long as we have a valid reference to the map, right? To our map, we know that we'll have a valid reference to the value inside of it. Because again, we're going to guarantee that all of those borrows are gone. Nobody has a borrow before we deallocate the map. Yeah, and the change in main now we're getting back a like value in main on line 13, right? It's a reference to an I32. So we can either dereference that because we know it's copied, that's fine, or we can change the 2 to be a reference so that our types line up. Both will work. Then we can run it, it should work. Are you still getting that lifetime issue?
Yeah, I am, but we can look at it after, it's a little bit different.
Yeah. So we didn't get it. Are there any questions? Sorry, I should ask that real quick. Any questions?
So the stat dimension is basically similar to a switch in
In Swift, yeah.
When you do the new function on hashmap, can you go to that? And when we do a new, where the heck? So, what the fuck is it initialized? Like, that's the thing, is like, at what point does it figure out what types were actual, concrete types were actually put inside of it? Or does it never need to? Because as long as everything in there just does it implements not the traits that we specify, it's fine. And
as far as like when it's type checking, when the compiler is type checking new right here, it's looking where you're using K and V, and it figures out, okay, this vector has to be a vector of pairs of K and V, but there's so that's
pretty
fine.
much it's happening like I have in main, I'm doing like let pairs and I'm inserting them into the map, and then like that's where
it figures it out.
Concrete figures out the concrete types. And so like when it's compiled, it will not do the Swift thing where it will do a generic. It will not just do it generically for any type that, but it will actually figure out the concrete types and define the functions, like actually implement the functions, the generic functions in terms of those concrete types that actually call into it.
Yeah. And in most languages, what happens is all this generic stuff happens at runtime where it figures out where it needs to go.
It's just all pointers.
Yeah, in C++ and well, in some C++ and some Rust, like when you're using generics like this, it happens at compile time in a process called monomorphization, which basically looks at how you're using these generic functions and then creating concrete functions for concrete types. So it looks, I'm using it on these integers, whatever it decides to use them as. And it will implement, some new RMAP for I32 or whatever, who knows? I don't know what the naming scheme is, but it'll actually put that in the binary. And if we use RMAP for some other types, there would be a new function for, string or whatever. Cool. Which means generics can bloat your binary. You have to know that every time you use a different concrete type for RMAP, it will create new functions for that. So you will have different functions depending on it. But
what happens if you define a library, for example, and in the library in the public, you publicly expose a generic interface, and then and it's a binary library, right? And then you pull it into another application, and then you use that generic interface. You can't.
which is how would it know?
Well, that's what I mean. Like Swift allows it to happen, right? Because
I assume the compiler will just not generate any functions because nothing called those generics, right? So they're just not there.
So you don't expose, pretty much, if we were making an SDK, right, we would never expose generic functions in our public interface.
The only way that you can publicly expose generic functions is if you're creating a Rust library, because then obviously the Rust library will eventually be compiled by the Rust compiler who understands how to make these things work together. But if you're going to create, you cannot create generic functions that interface out to C, for instance.
That's super interesting. By the way, yeah, that's super interesting. Did you have anything else you want to talk about today, or should we say thanks for next time?
Yeah, I think like we're already 8 minutes over, so we'll call it a day for now. We can available for questions and stuff like that afterwards. But we went through a lot of stuff today. This is a really good foundation. There's only a few more advanced use cases of things around borrowing and ownership that we have to go over to get a more solid understanding of it, but this will get you a long, long way. If you're interested in learning more, then we should meet again.